Hi guys, so today we are going to do our last parent function of the year. So as you guys have seen a lot this year, we've done a lot of different parent functions and we've done transformations to those parent functions. Well, today is the last parent function and the last day that we're going to look at transformations for a new graph. Now next week, or the week after next, we're going to go ahead and review all these parent functions that we've done so far. But there will be no more new parent functions in this class. Now you'll see a couple new ones in pre-cal, but this is the last one for Algebra 2. So what we're going to do is we're going to look at the log parent function. And the log parent function, as we've mentioned before, is the inverse of the exponential parent function. So to review, let's talk about what the exponential parent function looked like. Okay, if the base was greater than 1, it showed growth, and it had this general shape to it. The points that it went through were 0, 1, 1 comma the base, -1 the reciprocal of the base, and 2 base squared. It also had a horizontal asymptote at y equals 0. The domain was -infinity to infinity, and the range was from 0 to infinity. Now the log graph, like we said, is the inverse of this graph, which means the x and y's are going to be flipped. So instead of going through 0, 1, this graph will go through 1, 0. Instead of going through 1 comma the base, it'll be base comma 1. Instead of -1, 1 over the base, it'll be 1 over the base, -1, and base squared, comma 2. Now, it's also going to have an asymptote, but this is the biggest difference and the easiest way to tell these two graphs apart. An exponential function is going to have a horizontal asymptote. A log graph is going to have a vertical asymptote. Because the problem is, once you start reflecting these and transforming these, the shape of the graph, it's really kind of hard to tell which one it is. So you really need to look for the asymptote to give you a big clue on whether or not it's an exponential or a log graph. All right, so let's go ahead and sketch that graph. So again, we'll go through 1, 0, whatever the base is, comma 1. So the general shape will look like this. And again, you can kind of see how if that asymptote wasn't there, it'd be kind of hard to tell the difference between that graph and if you had a reflection and a few changes to your exponential function. So domain for this graph, it does not touch the asymptote, so from 0 to infinity. We also know that's true because the argument can't be negative. And then the range is -infinity to infinity. And if you notice, like we've talked about before, the range of the inverse is the domain of the other, and vice versa. Now, just like with exponential, for logs, it also matters the value of the base. So typically the shape we're going to look at is the one we just had. But again, that's going to be true if the base is greater than 1. If the base is between 0 and 1, it's going to look a little bit different. So let's again talk about exponential. Exponential, even if the base is between 0 and 1, it still had the same points. It still had 0, 1, 1 base, -1, 1 over the base, and 2 base squared. It still had a horizontal asymptote at y equals 0. None of that changed. But because the base was a fraction, 1 comma the base would be a smaller value, and the reciprocal of the base would be a larger value. So that graph would look like it was showing decay. But domain and range and those key points really didn't change. So very similar for log. It's still going to go through 1, 0, base 1, 1 over the base -1, and base squared 2. It's still going to have a vertical asymptote at x equals 0. But because of the shape of the graph, 1, 0 is still a point. But let's say that base was 1/2. Well, 1/2 comma 1 would be over here. And then 1/2 squared would be 1/4 2, so a smaller value. And again, it's going to keep getting larger as it goes towards my asymptote. So the shape of the graph would look different if that base was between 0 and 1. Domain and range, though, are not changing. All right, so this is your log parent function. Again, depending on the base, the shape may look different, but it's still going to kind of have those 4 main points. And again, that vertical asymptote. That's really the important thing to remember here, is that the log graph has the vertical asymptote, the exponential function has the horizontal asymptote. So let's just sketch the parent function with 2 different bases so you guys can again see that general shape. So let's just say we're sketching the graph log x. Well, that has a base of 10. So this is going to go through 1, 0, 10, 1. It would go through 102. That's not going to fit in our graph. and then it would go through 1 over 10, negative 1. So we can go ahead and put those points on there, at least the ones that will fit. It still has a vertical asymptote at x equals 0. And this is your graph. Domain is from 0 to infinity. Range is from negative infinity to infinity. All right, let's look at the next one. Same idea, different base. Ln has a base of e. So it should go through 1, 0, base, comma 1, so e, comma 1, or 2.7, comma 1. Base squared, comma 2, so 2.7 squared, which we said was about 7.3. And then 1 over the base, negative 1, which again, going to be a pretty small fraction that's going to be on there. Hasn't been shifted or anything, it's still the parent function, so we still have that asymptote. So 1, 0, about 2.7, comma 1, and 7.3, comma 2. And that is my graph. All right, so from this point, we're going to go ahead and look for the last time, at least for the sake of a parent function, a new parent function, the same chart you've seen too many times this year. So a shift to the right. Anything that's happening horizontally is going to happen within the argument. So if it's in the argument, it's horizontal. So if I had f of x, again, base doesn't matter. If let's say this was log of x minus h, that's going to be a shift right. If I have log of x plus h, that's going to be a shift left. Horizontal stretch or compression, again, it's going to be inside. So any value that's multiplied on the inside. Same thing with a reflection over the y. That is going to be a negative on the inside. Again, there is going to be a difference in the way your graph looks if it's reflected over the y-axis. So I know for our earliest graphs of the year, there wasn't much, but there will be for these log graphs. All right, shifting up. Anything that's not in the argument is going to be vertical. So if I have log x and then outside the argument, I have plus a value or minus a value. Those are going to be your vertical changes. Okay, multiply it out front. Okay, that's going to be your vertical stretch or compression. A negative out in front, that's going to be your reflection over the x-axis. Again, just like with exponential, we're not really shifting. When we shift that 0, 0 point, we're not really shifting an actual point in the graph. We're shifting our new origin. I kind of like the center of the asymptote. It is where your asymptote is going to be located, but again, it's your new 0, 0. Okay, it's the new origin. So everything will be in relation to that new point. All right, now if you want to see these transformations, there is a Desmos activity. You guys have to do the last couple slides as part of your practice, but the first, I think about 7 slides or so, is just for you guys to kind of move those sliders and see how these different changes look on your graph. So you're welcome to go ahead and just play with those. The only ones you have to do are the ones at the end. There's like 2 multiple choice and 3 where you have to write the equation. All right. So let's go ahead and actually sketch a graph with some transformations. So the first thing we need to determine, what's our base? Okay, our base is 2. I'm going to go ahead and list my transformations. I've got a vertical stretch, and I've gone left 4 and down 1. So if I've gone left 4 and down 1, that means that's where my new origin is. That's my new 0, 0. Since this is a log graph, that also means that's where I'm going to have my asymptote. All right, so then since my base is 2, let's list those parent function points. It's the inverse of exponential. So 1, 0, base 1, base squared 2, and reciprocal of base negative 1. All right, so those are how I'm going to move in relation to that new center. So from negative 4, negative 1. But how this has changed is that it has been stretched vertically. So that's going to affect the second number. So I'm going to multiply those by 3. And then this is how I'm moving from that new origin. So from that point, I'm going to go right 1 and up 0. From that new origin, I'm going to go right 2 and up 3. From that new origin, I'm going to go right 4 and up 6. And then I'm going to go right a half and down 3. And then that will be your new log graph. Domain here is going to be from negative 4 to infinity. range is going to be negative infinity to infinity. And that is going to be true for all log graphs. Because again, it's the inverse of exponential. And every exponential had a domain of negative infinity to infinity. All right, let's look at another one. All right, again, let's start by determining the base, and let's determine the transformations. So my base is 3. That means the parent function points would be 1, 0, base 1, base squared 2, and then 1 over the base negative 1. All right, before we list our transformations, I'm going to go ahead and factor out that 2. So now that that 2 is factored out, I can see my transformations. This has been reflected over the x. It has a horizontal compression. It's gone left 5 and up 4. So since it's gone left 5 and up 4, that's your new origin. That's where your vertical asymptote is. And that's where your parent function points are in relation to. So since I'm reflecting over the x, that's going to affect the second number. And then since it's horizontally compressed, that's going to take that first column and divide those values by 2. So this would become 1/2, 3/2, 9/2, and 1/6. So from that new origin over a half up 0, I'll make it a different color so it's a little easier to see. It's going to be pretty close to that point. Over 1.5 and down 1. I'm going to go over 4.5 and down 2. And then I would go right 1/6 and up 1. So not going up very much. And that is my log graph. Domain here is going from -5 to infinity. Range is from negative infinity to infinity. All right. So now, the last thing we're going to look at is domain. So now we did do domain in every graph we just looked at. However, I want you guys to find the domain for some graphs that you're not necessarily going to have to draw. Okay, so something like A and B, you're not going to need to draw that. Okay, you can't really tell the transformations, and these are going to have kind of an interesting shape to them. But what we do know about the domain, we can determine that even if we don't know what the graph looks like. So because what we know is true about a log is that the argument has to be positive. So if I want to find the domain, well, the domain of the log is wherever the argument is positive. So that means the domain is everywhere that whatever is in the parentheses is greater than 0. Now, not greater than or equal to, okay? It has to just be greater than 0. So all I have here really is just reviewing how to solve an inequality. So what I'm going to do is I'm going to take whatever is in the parentheses, and I'm going to make it greater than 0. So this first one's a polynomial, so or a quadratic. Like I said, it's a polynomial as well. If you remember how we solve quadratic inequalities, the first thing we need to do is we need to find the zeros. So I'm going to factor. This is going to factor into, let's see, we've got 3x and x. So this is going to be -3 and +2. So that's how it factors, which means the zeros are going to be at -2/3 and 3. And then what we did was we picked those test points to determine where this graph was positive and negative. Well, you also could think about the shape of the graph. It's a parabola that opens up. So it's obviously going to be positive, negative, positive. But you also can pick those test points just to make sure. Like if I plugged in 7, that would be a positive and a positive, which is positive. So then we look back at our question. We want to know which greater. So our answer is the positive intervals. The positive intervals are from -infinity to -2/3 and from 3 to infinity. It is parentheses in all these values because your argument has to be greater than 0. It can't be 0. Because if you think about it, if you have log base 2 of 0, can you think of what to raise 2? You can't raise, there's no power you can raise 2 to 2 in order to make it 0. So the argument has to be greater than 0, not greater than or equal to 0. All right, same idea with b, except this time it's a rational function. So same thing, this is just reviewing rational inequalities. So the way we solved those was we found the x-intercepts, which was when the top equals 0, and we found the vertical asymptotes, which was when the bottom equals 0. Again, we picked some test points. Let's say, for example, I plugged in 0. Okay, that would be a negative over a positive, which is negative. If I picked a large number over here, okay, if I picked 7, that would be a positive over a positive. and I get that pattern. Again, I'm looking for where my graph is positive. So this is negative infinity to negative 1/4 and 2/3 to infinity. And that's my domain. So again, you don't need to know what this graph looks like. We're not sketching these graphs, but we can determine the domain by just taking the argument and setting it greater than 0.